Hello and welcome. In this series of lectures in week 1, we've been looking at the basic concepts of probability theory, and so far you've seen sample space, outcomes, events, and now we're going to see the probability, what is called probability itself, that will enter the picture now as part of the of this whole theory. Okay. So before that, let's just reflect a little bit on what all this is. We are really, we want to model something that happens, some phenomenon or some event or something that happens in reality in a statistical way, right? So we know that we cannot do deterministic model, we want to do statistical way, so we're working towards it. And we came across this notion of events, and that seems interesting, and events are very useful to understand. And now we want to associate a mathematical value of chance to that event occurring. Okay. So quite often, once I describe an experiment to you, and once I describe and define an event in that as a subset of that experiment's outcomes, you have a sense in your mind as to whether or not it will occur. Okay, what is the chance that it will occur? So you may get a sense that it's a very low chance of that occurring or a very high chance of that occurring. So intuitively you may know this. So here's a few examples to show you how to do this. Supposing you toss a coin, right, and it's a fair coin, and then for instance over several tosses you appear heads, you think that heads could occur maybe half the time, right? So this is sort of intuitive, right? So that's why people use coin toss before every test match or a cricket match to decide who's going to bat first. They expect it to be fair in some sense. Okay, so maybe you think every time 50% chance of heads, 50% chance of tails, right? So that's something that you associate with. And many of you might have played cards, and you might have 4 players playing cards. It's very popular to have 4 players playing cards, and you distribute the pack to everybody. And I'm sure collectively among us, we would have never had, unless it was specifically somebody was cheating, it's almost, you would have never seen a case where somebody got dealt all 13 cards from the same suit. Okay, it would literally, it would be a huge surprise if that happens, right? So you should of course shuffle the cards properly and then deal. If you don't shuffle, then anything can happen. But if you shuffle the cards properly and then deal it out, it's a really very, very low chance that one player gets all 13 cards of a suit. All 13 spades. What's the chance of anybody getting that, right? Oh, here's another event. Okay, maybe a little bit different, not a toy experiment, something that happens in real life, right? The Football World Cup, right? And what is the chance that India wins the Football World Cup? You have a sense of that. I think it's not very high, definitely. Okay, but chance of India winning the Football World Cup is not that high. Okay, this is just based on our collective experience. It could happen, but it'll be a big surprise if it happens. On the other hand, if you look at the Cricket World Cup, chance of India winning, one can never say it's like 90% or anything, but it's still high, right? There are several good teams, but it's relatively higher than the chance that India would win the Football World Cup, like for instance, just to give you a comparison. Okay, so what am I trying to say here? So given an event, somebody gives you an experiment and defines an event, we have a sense of the chance chance of that event occurring. Okay, so in the entire goal of probability theory is to give you a reasonable way to assign proper values of chance to these events in an experiment. Okay, so you have a sample space, you have events. How do you assign probability or the chance of that occurrence of that event? How do you give a number to it? How do you work with it? How do you give in the sense, how do you work with numbers which represent chance? Okay, so that's how we build up a probability theory. We'll see that it has a lot of interesting ingredients, and it's central to the study of data science and statistics in some way. Okay, so before that, I want to take a quick detour and point you to what is a mathematical theory, right? So probability theory is a mathematically developed theory. So what are the ingredients of a mathematical theory? So I'll go through this real quick. It's just a little bit of philosophy to get you used to how we'll see things. So typically in a mathematical theory, you want to define basic objects of interest, and this will come from other prior fields. Like for instance, in probability, it comes primarily from set theory, right? So you have the set which is a sample space, and you have subsets which are events, isn't it? So we will soon define probability, and that will also be an object which you're familiar with. Okay, and then once you define the objects of interest precisely, you will assume a few things. You will put down a few conditions. Okay, I say assume a few things, as in when I assume a few things to hold, I'm saying those conditions are valid, right? So we'll put down a few axioms, which are either you can think of them as conditions that you have to always satisfy, or they are assumptions that we make about the objects that we have. Okay, and then once you do that, that's it. You can't do anything else intuitively. Okay, so of course your intuition plays a role, but you have to back up everything else with logical proof. Okay, so that's how a mathematical theory works, and definitely the logical proof part, many people get turned off by, it's a bit scary sometimes if you're not used to it, to get into it. But mathematical theories have had tremendous impact in the world today, right? So some of the theories have been so successful, particularly when the axioms are very natural. They respect your intuition, of what you're trying to model, and it ends up being very, very widely applied in such a big area. So for instance, if you look at analysis, algebra, there's applications all across in so many different areas. All of that, all the mathematical theories are built in the same way. There's a few objects of interest, a few axioms or conditions that have to hold in the beginning, then after that everything else is logical proof. Okay, so in this class we will not do the theory in a mathematical way. We're going to do it in a very applied fashion, but we won't really, we won't disrespect the mathematics, as in we will respect it, and when possible maybe I'll show you some proofs, just for saying, how is it that these things work. Okay, some arguments, maybe one or two lines. We won't be that rigorous about it, but at least just hand waving arguments on why they work like this, right? So it's sort of interesting to do this. Okay, so this is how any mathematical theory is. Probability theory is also like that. What are the objects of interest in probability theory? I gave you 2 or 3 objects already. 2 objects: sample space and events. These are very important objects. The third important object which makes up probability theory is probability. Okay, so it's called probability itself. Probability is a function. Usually we'll denote it P. Okay, and what does it do? A function is what? Function will have, there is a argument that the function will take, and there is a value that the function will assign it to, right? So function is always, you think of it as f of x or something like that. So x is the variable that's the function operates on, and you get the function's value, right? So that's the function. It takes you from one set to another set. Okay, you can call it domain and range if you like, right? So it goes from domain to range. You have 2 sets. The function tells you how to go from, how to map one point from this set to another point in that set. Now, what kind of function is probability? The argument is an event. Okay, probability takes event as input in some sense, right? So that's the probability function. The input to this function is an event. You give this probability function an event. What will it tell you? What is the output? What is the value of the function? It is some real number between 0 and 1. Okay, what kind of function is it? Once again, the function takes as input subsets of the sample space, which are events. Okay, and its output is a number between 0 and 1. Okay, so these 3 things together, probability, probability function, events, sample space, events, probability function. These 3 together, make up something that people call generally as the probability space. Okay, so it's called probability space. Of course, there's experiment and outcome, but they are not mathematically precise objects, right? So these 3 are mathematically precise objects: sample space, events, probability function. These 3 make up the probability space. Okay, so these 3 together should satisfy 2 axioms, 2 very important axioms. I will specify it in the next slide or 2. Okay, you'll quickly get it. So without satisfying those axioms, we will not continue, right? So at that point, we don't have a valid probability space. Okay, a probability space will be valid only when it satisfies 2 axioms that I'm yet to describe. I will describe them soon enough. But before that, let's just dwell on this probability a little bit. What is this? Okay, now as a mathematical object, this is just a function from the events to the the line segment between 0 and 1 on the real number line, right? So between 0 and 1, some value between 0 and 1. So that is the function definition, just mathematically. But what do we want it to be? We want the value assigned by the probability function to be something like the chance of the event occurring. Okay, that's our intuition. We want the probability function to represent the chance of the event occurring. So if you have an event A and you give it to the probability function, the value it spits out, the value that it gives you, you are hoping represents the chance of that event occurring. Okay, so that's how you want to build the theory. That's how we want to do it. Okay, so that's how you want to use the theory. Okay, let me be very precise here. You build it differently, but that's how you want to use this theory. Okay, so in general, the values between 0 and 1, you can also express it as a percentage, right? So any value between 0 and 1, you can express it as a percentage. If it's 0.9, you're going to say it's 90%, like that. It's easy to do. Generally, even what is the assumption here? Higher value means higher chance, right? So if the probability of an event is 0.9, then that has a higher chance of occurring than, say, a probability of an event which is 0.1. So that event may not occur that often. Okay. The values 0 and 1 are special. If it's 0, if an event has a probability of occurrence 0, then it will never occur. If the event has a probability of occurrence 1, then it always occurs. Okay, so it's always true. So I've put a fourth point there, which is a warning. So this kind of associating a meaning comes only when you want to apply the theory to some particular case. The theory itself doesn't care. As far as the theory is concerned, you have a set which is a sample space, you have a bunch of subsets which are events, and then you have a function from the set of events to the real line between 0 and 1, and that's it. That's probability for me. I don't care whether it connects to an IPL game or throwing of a die or whatever. My theory will give you enough tools to work on, and the person who comes in to apply will attach the meaning to all these things. Okay, so this dissociation you should keep in mind. Okay, so I'll give you some examples to sort of drive home this point later on. Okay, so at this point we've identified all the ingredients of the theory. Everything has been defined. Sample space, events, probability together, they are called the probability space. Once again, I want to point out experiment and outcome are not very precisely defined mathematical objects. They don't enter into the theory itself completely. We work with sample space. So once you have sample space, everything about the experiment and outcome are known. Experiment and outcome, the way you set it up is where the physical part comes in. Someone who comes in to apply the theory will start setting up an experiment and thinking about outcomes, and then grouping them into a set which is a sample space, etc., etc. Okay, so that's probability. I haven't told you the axioms. Those are the two important things. The axioms make or break everything, right? So if you don't have the axioms, you don't have a theory. So I have to tell you what the axioms are, but before we jump into the axioms, let's try and motivate the axioms. So where will the axioms come from? How do you why do we need it, sort of? Why does it make sense? So like I said before, probability function simply assigns a value to an event, and you want it to represent the chance, something like the chance that the event occurs. Right? That's what you want. Okay. So these axioms, what they will do is they will place conditions on the probability function. They will say, not every function is a valid probability function. For your function to be a valid probability function, here are the two conditions it needs to satisfy. That's what the axioms will say. Now, why do you need those conditions? You need those conditions. I've sort of put it out here in some way. There are various other ways in which people think of these things, but so intuitively, the axioms should be natural in some sense. When you have a certain relationship between events, the way you assign probability to those events should respect that relationship, right? When you combine events, it should be easy for you to work with the probabilities in that the probability function gives. All these things should be ingredients in the theory. Otherwise, it makes no sense. Okay. Here are a few more basic scenarios, right? So, for instance, if A is a subset of B, right? P of B, which is the value assigned by the probability function P to the event B, right? Should it be higher than P of A or lower than P of A? What does your intuition tell you? What's the natural intuition? If you have A being a subset of B, and you have P as the probability function, P is associating a value P of A to the event A as the probability of A, P of B as the probability of B. If A is a subset, you want intuitively P of B to be higher than P of A, right? So these are conditions. So this might be a condition that you desire, right? So your probability function should be like that. Okay. So likewise, there are more complicated things. I mean, if A and B are two events and P of A and P of B are known, it may place some restrictions on P of A union B, right? So there may be some restrictions like that. So you can imagine why. So these kind of things have to be respected by the axioms. The axiom should enforce conditions on the probability function so that these things naturally apply to anything that you come up with. Okay. Now here are a few more basic questions. So what's going to be the probability of the empty set in any probability function? What should be the probability of the empty set? We know empty set is an event, right? So what probability should be assigned to the empty set? Similarly, what probability should be assigned to the entire sample space, right? So you know entire sample space together is an event, right? It's a valid event. So what probability should you assign to that? Okay. We also saw A and B being disjoint is an important thing in probability. When you look at events, being disjoint gives you strong conditions. So if they are disjoint, what can we say about P of A, B, P of A, P of B, P of A union B? You know, it's a special particular case, right? We know P of A intersect B has to be 0, right? If they are disjoint, maybe, right? P of empty set, there's nothing in it, right? So what about union? Are there other interesting conditions like this? And how do you, I mean, there can be so many numerous conditions. How do you put all that into two axioms, right? So that's the power of the theory. Okay, so people have worked over the years, refined them, and got just two axioms now. There are just two conditions that you have to satisfy to be a valid probability function. And once you satisfy that, all the intuition, all the natural intuition about how events combine, relationship between events, all that will be respected. Okay, so that's the power of the axioms. I mean, I'll state them, they'll seem very simple and intuitive to you, but their real power is that they enforce conditions that ensure that theory supports the practice in a nice way, or theory reflects the practice in a very obvious, easy way. It's easy to make, let me put it this way, maybe this is a better way of putting it. The axioms ensure that it's easy to make theory comply with the practice, or theory reflect the practice in a close way. Okay, so that's the power of these axioms. Let me give them to you. You will see that they are very simple, and at the same time they are very powerful. Over the rest of the lectures, we will see how to use these axioms in interesting ways. Here are the axioms. Okay, so these are called the probability space axioms. The definition, I'm sort of repeating the definition of probability again for you. Okay, this is the proper definition because the last time I did not define the conditions that it needs to satisfy. So probability is a function P that assigns to each event a real number between 0 and 1 and satisfies the following two axioms. Okay. P of S, probability of the entire sample space, is going to be 1. Okay, so that's the first axiom. You have to ensure that for the entire sample space, you associate a probability 1. Otherwise, it's not a valid probability function. Okay, it's not a valid probability space. The second axiom is what's intriguing, and how that it could be the most central axiom in probability is it sort of took time. It was not very easy to come up with this. So here's the axiom. Supposing you have a collection of disjoint events. Okay. Now I'm going to write them as E1, E2, E3, ... Now how many events you can say? You may ask me how many events. Is it just 2 events, E1, E2, or should it go on and on? It turns out you could have either a finite number of events, or you could have infinitely many. It can keep on coming one after the other. It has to come E1, E2, E3, like that. Like that it can keep on coming, and you can have an infinitely many number of events like this. Okay. So the second axiom is what's most interesting. If you have a collection of disjoint events, E1, E2, E3, so on. Okay. What is this so on? How many can you have? You could have a finite number. It could go up to 10 and stop, or it could keep on going 10, 11, 12, 13, 100, 1000, 10,000. Never ending sequence, right? But it's in that sequence. Okay. So it can either be finite or it can be going on and on and on. But they all have to be disjoint. Okay. There's no question of being any intersection between any of them. If that were the case, then the probability function, okay, should assign values to events such that P of E1 union E2 union E3 union so on Okay, so what is inside the P here? Let me just show you on the pointer. What is inside the P here? It's the union of all these disjoint events that you have. Okay, either E1 occurred or E2 occurred or E3 occurred. You know, union is like or, right? You have a bunch of disjoint events. Disjoint is a very key word here. And you have E1 union E2 union E3 on the left side. So what is P of that? The probability value assigned to the union of all those events. Okay, so we saw before how you can have disjoint events and how you can take unions of events. Okay, they are all events again, right? You take union of two events, you get another event. It all becomes events again and again and again. Now your probability function assigns probability to all events. So if you have a bunch of disjoint events, it will assign probability to each of these events. It will also assign a probability to the union of all these events. Now the second axiom is saying the probability function should assign values such that the values that it assigns to E1, E2, E3, etc., if you add them all up, look, notice what's happening on the right hand side. On the right hand side, I'm taking each of the individual probabilities, P of E1, P of E2, P of E3, etc. I'm adding them all up. That sum should be the exact same value as what? As what you have on the left hand side here. What do you have on the left hand side here? It's the probability assigned to the union of all these events. Okay. So if you want a very simple axiom here, simply say E1 union E2. Okay, drop everything else, right? It says go on and on, forget about E3 onwards. It says if E1 and E2 are disjoint, P of E1 union E2 is P of E1 plus P of E2. It has to be that way. The probability function has to do that. It doesn't have any other way of doing it. Okay. So first thing I want to say is these are very, very intuitive and simple conditions, and you can see why they are simple conditions, right? The probability of the whole sample space being 1 is sort of obvious, right? If you define the whole event to be the entire sample space, any outcome is okay with you. So what chance is there that something happens? Something will happen for sure, right? So that's how your experiment works. So you should assign the value 1 to the entire sample space. That's very clear. Okay, right? So remember when I say P of S, what do I mean? I'm seeing S as an event, right? The event of the entire sample space together is actually a subset of the sample space. That subset should have a probability of 1. That's the first condition. What does the second condition tell you? You have two events, let's say, which are disjoint. You put a probability here, you put a probability here. If you look at the union of those two, the probabilities should clearly add, right? So you have a 10% chance that something happens, another 20% chance of something else happening which has no intersection here. Either this or this will happen with 30% chance. Right? It has to respect that, isn't it? So it's a natural law that's coded into mathematical language here as axioms. Okay, so most people, when I describe the natural laws, seem comfortable, right? So something will happen when you say probability of the entire sample space, it should be 1, and then when you have disjoint events, the chances add. It's clear, but sometimes the precise mathematical language is a bit troubling. But don't be put off by it. Try to understand it, and it's actually very comforting once you get over your initial difficulty, because mathematics is very precise, and precise things are much more easier to understand than imprecise things. Okay, so look at how this language captures the intuition. Okay, so axioms are intuitive, and they put down conditions which have to be satisfied by every probability function. If the condition is not satisfied, it's not a valid probability function. The theory will not do meaningful things after that. Okay, so we'll see how to put them to use, and it's very, very useful. Okay, so I'm going to show you next a few examples and sort of argue that well, the theory has just 3 objects and 2 conditions, but it's not very easy to get started with this, right? So we need more simpler things to start using this theory. And for that, we will start making some deductions. Okay, so let's see a few examples to see where the theory is sort of becoming difficult to use, right? So let's take the first experiment to be tossing a coin. Okay, sample space is h comma t. I've been writing heads and tails so far, but we can write capital H comma capital T. Capital H stands for heads, capital T stands for tails, right? So that's your sample space. The first probability function. Okay, so what I'm going to do is I'm going to show you multiple probability functions. For the same sample space, I'm going to show you multiple probability functions and then ask you does this function satisfy the axioms? There are two conditions in the axioms. The question I'm going to ask you is, do they satisfy does this function satisfy the axiom? Okay. What is the first function? The first function assigns a value of 0 to the empty set, assigns a value of 0.5 to heads, okay, which is the subset just h. Remember, for h comma t, there are only 4 subsets, right? There are only 4 events. What are the 4 events? Empty set, the entire set h comma t, h alone, t alone. So you have to just assign 4 probability values and they have to be consistent with the axioms. Okay. So to the empty set you can assign 0. To the entire sample space you can assign 1. You have to assign 1 there, right? If you don't assign 1 there, you immediately violate it. And then you put 0.5 here, 0.5 here. So how do you go about checking the axiom? How do you check the second axiom? You have to find disjoint sets, isn't it? You have to find disjoint subsets, right? What are disjoint subsets? H alone and T alone, let's say, are disjoint subsets. So what is the union of the two disjoint subsets? The entire set h comma t. So you see it adds up. So probability of h plus probability of t equals probability of h comma t. Okay, it works out. It's correct. Now I want to generalize this a little bit. The next second bullet point there shows you, maybe I should use my pointer here. The second bullet point shows you a more general case than this. I take a value p, small p, which is some value between 0 and 1. In the previous thing I took 0.5. I'm going to take, let's say, any other value. It could be 0.2, 0.3, 0.9, 0.8, any value. And I'm going to assign probability of heads to be p and probability of tails to be 1 minus p. And probability of empty set I'll keep as 0. Probability of h comma t I will keep as 1. This is another probability function on the same sample space and same events. Okay, there are 4 events and this is another probability function, and this also is a valid probability function. You can check, you can do this quick check. P of h plus p of t should be equal to p of h comma t, right? So that we know from the second axiom. The second axiom is satisfied. Okay, p 1 minus p, you add these two, you get 1. Okay, of course it has to assign a value between 0 and 1. That is also happening. So I've given you here another function which is invalid. Okay, just to show you that not every function is valid. You can't think of any function. Okay, so it assigns 0 to empty set, 1 to the entire sample space. Let's say we put 0.5 to h and 0.6 to tails. This is not a valid probability function. Why is that? You do p of h plus p of t, you get like 1.1, which is clearly wrong. It should be 1 because p of h comma t is 1. Okay, so hopefully this gave you a quick glimpse at how these probability functions look. They are just values between 0 and 1 assigned to the subsets of the sample space. How many ever subsets you have to assign a value to all of them, and then you have to check all these conditions, right? The first axiom is very easy to check. The second axiom is tough to check, right? There are so many disjoint subsets, and where do you go checking everything? For h comma t it was very easy. There was only really one check you have to do. But in general, how do you do it? It doesn't seem that clear, right? Okay. Let's look at a slightly more complicated example. You'll see the problem with this when immediately when I see a complicated example. And you need not even go that big. Let's just look at throwing a die. Okay, it's 1, 2, 3, 4, 5, 6. There are 6 elements in the sample space. There are 64 events. Forget about even checking whether the axioms are satisfied. How do you even specify the probability function? What do I mean by specify? So in the previous case, I could write the probability for every event. How do I write the probability for every event? There are 64 events. I have to make a big table of all the subsets and then put one value against each of these things. Okay, it's going to be really tough after that to ensure the axioms are satisfied. There are so many disjoint subsets here. I have to make sure I don't violate all of them. Okay, so all this is not giving me an easy way out. The theory seems hopelessly complicated at this point if you don't make use of the axioms and simplify your work. Okay. So we will try and address these questions in the ensuing lectures of this week. We will come up with an easy way to specify a probability function and ensure that it's valid. Okay, so I'll give you a very easy way to do it. It's not that hard. I mean, I just asked you a simple question. You'll see it's a very easy way of answering it. And we'll see several types of sample spaces and all that. And we will use only the axioms. We won't do anything else. Okay, everything else will be deduced from this point on. Okay, that's the power of the theory. That's how the theory works, right? So you had your basic objects, sample space, events, probability function. You have your 2 axioms which place conditions on the probability function, and from now on we'll start deducing. How to, the first thing we have to deduce is how to easily specify a valid probability function that will definitely be valid. How do you specify that? Okay, the answers are different based on what type of sample space you have. The first type we'll consider is a finite sample space, like for instance a finite number of elements in the sample space. How can you go about specifying a valid probability function? Okay, so we'll see that in the ensuing lectures. Thanks a lot for your attention.